Yeah, thanks, Mike. I've been involved in software metrics on and off for many years. And during that time, my views about what's feasible and useful have changed quite significantly. Today, I'm going to provide a summary of what those changes are. I'm going to run through 10 fallacies. Now, collectively, this is going to enable me to provide a lightning history of software metrics. The good news is that globally, software metrics has provided some decent benchmarking information about software projects, and locally has led to managers having greater control over projects. The bad news is that traditional metrics and models don't provide the kind of quantitative information that software managers have a right to expect. And I'm talking about things like this. For a problem of this size, and given these limited resources, how likely am I to achieve a system of suitable quality? Or how much can I scale down the resources if I'm prepared to put up with a system or product of a specified lesser quality? And then finally, if some model, software metric, predicts that I need, say, 40 people over 2 years to build a system of this kind of size, but I've only got funding for 30 people over 1 year, if I can't sacrifice quality, how good do the staff have to be in order to build the systems with those limited resources? Now, this is all about quantified risk assessment to help decision making. I don't think software metrics has traditionally properly addressed this true objective. I'm going to try and convince you that the true objective can be met by considering causal factors in the software process. And this can lead to improvements in very specific activities like defect prediction and more general ones like project risk management. My talk can include a simple example of one of these causal models in action, and that's a simplified version of the kind of model that's been used extensively with great effect at a number of different blue-chip organizations. I want to start with a fallacy that was raised by one of the all-time greats of software metrics. That's Bob Grady at Hewlett-Packard. Bob was responsible for what I believe was recognized as the first true company-wide metrics program. And his excellent 1987 book about software metrics programs with Deborah Caswell described the techniques and experiences associated with that. Now, in 1993, I was at a meeting where Bob told a very interesting story about that metrics program. He said that one of the main objectives of the program was to achieve process improvement by learning from metrics what process activities worked and what ones didn't. To do this, they looked at those projects that in metrics terms were considered most successful. And they originally felt that a key measure of a successful project was one which delivered high quality to the user, and the measure they used for this, like many other practitioners, was the rate of customer-reported defects. For example, the number of defects found by customers per 1,000 lines of code in the first 6 months of operation. So a project was classified as successful if it recorded significantly below average defect density. The really star projects were those that hit the magical defect-free target of 0 defects per 1,000 lines of code. So the idea was to learn what processes characterize those most successful projects. Now, it turned out that what they learned from this strategy was very different to what they'd expected. Instead of learning the answer to the big question, the projects that were identified in this way as success stories from the metrics data turned out generally to be anything but. They were projects that were either so bad they never got delivered to customers, or they got delivered but they were rarely used. So that's what explained the 0 or low defect rate. Now, the idea of a simple causal explanatory factor is very important to the main message that I'm going to convey in the rest of this presentation. So the next fallacy is that people commit to metrics because they believe it leads to process control and improvement. Now, in fact, while some individual evangelists might do so, this is generally false. Most industrial metrics programs or initiatives are typically a classic example of a grudge purchase. People normally only commit to some kind of a metrics program because they're forced to do it. This might be because of the need to adhere to a standard or a customer contract, or simply because of a higher level management demand that they've not bought into. Now, in these circumstances, it's unlikely that they believe it will truly improve things. Now, of course, where metrics are not universally agreed or understood, that is also true in all walks of life, not just for software project metrics. The next fallacy is that software metrics research is practically driven. In fact, software metrics research has been almost exclusively driven by academics, and much of this research has been inherently irrelevant to industrial needs. Now, I want to make it clear that I'm not assigning blame to unnamed individuals, because I'm as much, if not more, to blame than anybody here. For example, I, along with many others, did a lot of what we thought was clever mathematical work on software complexity metrics, by which I mean metrics that can be extracted from source code or high-level designs. Now, the problem is that in the context of real project risk assessment, these kind of what I call micrometrics are almost irrelevant. Rather, we should have been focusing on global complexity metrics, covering things like novelty of the problem, understanding, stakeholder involvement, through to organizational factors like scale of communications, subcontract management, things like that. Also, a lot of the research makes idealized assumptions about what data is going to be available. And as we shall see in a moment, a lot of naive statistical assumptions. But more than anything else, as I said in the introduction, much software metrics research has not delivered what managers and developers really want, and that is quantitative risk assessment and risk management. Now, I was looking at my own book earlier to see what it says about risk and decision-making in software projects. And in fact, guess what I found when I looked up in the index, the word risk and then the word decision? Absolutely nothing. Now, my only defense is one of ignorance. When I wrote it, I was wearing the same blinkers as most other metrics researchers. So, as I just said, the issue of use of statistics in software metrics work has been a problem. Now, by classical statistics, I mean that you collect as much data as you can, and you apply techniques like regression analysis to learn relationships, which then define your model for future use. The problem is, what do classical statistics approaches like that have to say about these kinds of questions? If we found no defects in 1,000 hours of testing, how likely will no defects be found in the next 1,000 hours of testing? If we typically find 20 defects per day, what will happen when we introduce a new type of testing? Or generally, how do I take account of any new information? Or additionally, what if the data collected is not from my organization and it's fundamentally different to what ours might look like? The problem with regression-based models in attempting to address questions like that, for example, the defect prediction, they've tended to dominate software metrics, but instead of predicting the future, all they really do is predict the past, which is a bit like driving by looking through the rearview mirror. So what do these typical metrics approaches look like? Well, actually, since the early 1970s, most serious software metrics activities generally work in this kind of way. There's something, I'm just going to pick up the, there's something why about a project that we really want to assess or predict. So that might be, for example, the effort required to complete the project, or, as in the previous example, the HP example, the quality delivered to end users. Now, the problem is that to measure or predict Y, you've got to find one or more things X that we can measure relatively easily.